crash course. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this crash course, we are going to take a deep dive into Google Cloud Platform networking. This is a hands-on, engineer-focused series designed for cloud architects, network engineers, and anyone preparing for GCP certifications or real-world deployments. GCP networking is built on a fundamentally different model than traditional on-premises networks or even other cloud providers. Google built its global infrastructure over decades, and the networking layer reflects that engineering culture, highly automated, globally consistent, and deeply integrated with Google's own private backbone. Over this course, we will cover the full networking stack, from the foundational VPC model, subnets, firewall rules, and routing, all the way through load balancing, cloud NAT, VPC peering, shared VPC, cloud interconnect, cloud VPN, and more. By the end, you will have a thorough, practical understanding of how to design and operate GCP networks at scale. In this first part, we cover the first 10 foundational topics, starting right now with an overview of what we will learn. VPC networks, core concepts. A virtual private cloud, or VPC, is the foundational networking construct in GCP. It is a logically isolated virtual network that you define within a Google Cloud project. All GCP resources that need network connectivity, compute engine virtual machines, GKE clusters, Cloud SQL instances, and more, are placed inside a VPC. One of the most important and distinctive things about GCP VPCs is that they are global resources. Unlike AWS VPCs, which are regional, a single GCP VPC spans all regions worldwide. This means a single VPC can contain subnets in US Central 1, Europe West 1, and Asia East 1 all at the same time, and those subnets can communicate with each other using internal IP addresses over Google's backbone, no VPN or peering required. Each GCP project comes with a default VPC that has one auto mode subnet in every region. For production environments, best practice is to delete the default VPC and create custom mode VPCs where you have full control over the subnet CIDR ranges and the regions in which subnets exist. The diagram shows this structure. The GCP project is the top-level container that owns the VPC. Inside the project sits the VPC network itself. The VPC then spans multiple regions simultaneously. In this example, US Central 1 and Europe West 1. Inside each region there are subnets, each with their own IP address range. Virtual machines and other compute resources are attached to subnets. This global, project scope model is what makes GCP VPC design fundamentally different from traditional networking. Google CP supports two VPC modes. Auto mode automatically creates one subnet per region with predefined CIDR ranges from the 10.128.0.0/9 block. Custom mode gives you complete control and is strongly recommended for production use because it prevents IP address conflicts and lets you plan your address space deliberately. Firewall rules. Google CP firewall rules control which traffic is allowed into and out of your VPC. Every packet entering or leaving a virtual machine interface is evaluated against the firewall rules associated with that network. Unlike hardware firewalls or traditional perimeter firewalls, Google CP firewall rules are implemented as a distributed, software-defined layer that is enforced at the hypervisor level on every virtual machine, meaning the firewall is always on and cannot be bypassed. Firewall rules have several key attributes. Direction can be ingress, meaning inbound traffic to a virtual machine, or egress, meaning outbound traffic from a virtual machine. Action is either allow or deny. Priority is a number between 0 and 65535, where lower numbers mean higher priority. Rules are evaluated in priority order and the first matching rule wins. A powerful feature of GCP firewall rules is that they can use service accounts or network tags as targets instead of IP addresses. A network tag is a string label you attach to a virtual machine. A firewall rule that targets the tag web server applies to every virtual machine carrying that tag, regardless of which subnet or IP address it has. This makes firewall management highly dynamic and scales beautifully in auto-scaling environments. The diagram walks through the evaluation flow. When a packet arrives at a virtual machine, Google CP checks whether the traffic matches the ingress firewall rules. It evaluates rules in priority order from lowest number to highest. If an explicit allow rule matches, the packet is permitted. If an explicit deny rule matches, the packet is dropped. If no explicit rule matches, the implied default deny rule at priority 65535 drops the packet for ingress. For egress, the implied default is allow. This is why all new VPCs have no default inbound rules. By design, nothing is allowed in unless you explicitly permit it. Cloud load balancing. Cloud load balancing in GCP is a managed, software-defined load balancing service that distributes incoming traffic across backend resources such as Compute Engine virtual machines, GKE pods, or Cloud Run services. GCP load balancers are not traditional appliances. They are built on Google's global infrastructure and are fully managed, meaning there is no instance to provision, patch, or scale. Google CP offers multiple types of load balancers designed for different use cases. The first major distinction is global versus regional. Global load balancers use Google's global Anycast network, meaning a single IP address can route traffic to the nearest healthy backend anywhere in the world. Regional load balancers serve traffic within a single region. The external HTTP and HTTPS load balancer is GCP's primary Layer 7 load balancer for internet-facing web traffic. It operates globally, supports URL-based routing, secure sockets layer termination, content-based routing, and integrates with CloudArmor for DDoS protection and web application firewall capabilities. The network load balancer operates at Layer 4, handling TCP and UDP traffic at very high throughput with low latency, and is suitable for non-HTTP workloads. The internal load balancer routes private traffic between services within your VPC without exposing traffic to the internet. The diagram shows the load balancing architecture. Client traffic from the internet arrives at the global Anycast IP. For HTTP and HTTPS traffic, it flows through the HTTPS load balancer. The load balancer evaluates the URL map to determine routing rules, for example, routing/API requests to a backend service running API servers, and other requests to a different backend service running web servers. Backend services contain instance groups or NEGs that are the actual compute resources handling the requests. Health checks continuously probe each backend to ensure traffic is only sent to healthy instances. VPC peering. VPC network peering is a GCP feature that allows two VPC networks to be connected so that resources in each VPC can communicate with each other using private internal IP addresses. The traffic between peered VPCs travels over Google's internal network, not the public internet, resulting in low latency and high security. VPC peering is commonly used when resources across different GCP projects need to communicate privately. For example, a shared services project containing internal tools, databases, or monitoring infrastructure might need to be accessible from multiple application projects. Rather than exposing those services through the internet or through a VPN, VPC peering provides direct private connectivity. There are important characteristics and constraints of VPC peering. Peering is non-transitive, meaning if VPC-A is peered with VPC-B and VPC-B is peered with VPC-C, VPC-A cannot reach VPC-C through that chain. You would need a direct peering relationship between VPC-A and VPC-C. Additionally, The subnets in the two peered VPCs must not have overlapping CIDR ranges. This is the most common operational problem with peering and reinforces the importance of careful IP address planning. Peering must be established in both directions. Project A must create a peering connection pointing to Project B's VPC, and Project B must create a peering connection pointing back to Project A's VPC. Only when both sides are configured does the peering become active. The diagram shows this relationship. Project A contains VPCA with its subnet range. Project B contains VPCB with its own non-overlapping subnet range. The VPC peering connection is a two-way relationship. The peering arrow goes from VPCA to VPCB, and a corresponding peering connection goes from VPCB to VPCA. Once both sides are established, a virtual machine in VPCA can reach a virtual machine in VPCB using internal IPs, and vice versa. The key limitation shown is the non-transitive boundary. VPCC, even if peered with VPCB, cannot reach VPCA without its own direct peering connection. Shared VPC. Shared VPC is a GCP organizational networking feature that allows a single VPC network, called the host project, to be shared with and used by multiple other GCP projects called service projects. This is the recommended architecture for large enterprises and organizations operating at scale in GCP, because it centralizes network management while allowing individual teams to maintain control over their own compute resources. In a shared VPC setup, the networking team controls the host project. They define the VPC, create the subnets, configure firewall rules, set up Cloud NAT, and manage all network-level resources centrally. Teams operating in service projects can deploy their virtual machines, GKE clusters, and other compute resources into the subnets of the host project's VPC, but they do not control the networking configuration. This model provides several significant benefits. Security and compliance teams can enforce consistent firewall policies across all projects from a single control plane. IP address management is centralized, eliminating the risk of overlapping CIDR ranges across teams. Egress controls, logging, and network monitoring are unified, and billing for network resources flows to the host project, while compute resources remain in their respective service projects for cost allocation. The diagram shows this architecture. At the top sits the organization node, which represents the GCP organization resource. Below that is the host project, which owns and manages the shared VPC. The shared VPC contains the subnets. For example, a front-end subnet, a back-end subnet, and a data subnet. Service Project A and Service Project B both connect to the shared VPC. Their virtual machines, Kubernetes nodes, and other resources are deployed into the shared subnets, but those projects themselves own only the compute resources, not the network. An admin in the host project grants each service project the permission to use specific subnets using IAM, allowing fine-grained control over which teams can deploy into which network segments. The key contrast with VPC peering is that shared VPC is a one-to-many relationship managed centrally. Peering is peer-to-peer between two VPCs. For enterprise scale, shared VPC is almost always the right choice. Cloud VPN, HAVPN and Classic VPN. Cloud VPN is Google CP's managed IPsec VPN service that creates encrypted tunnels between your on-premises network or another cloud environment and your Google CP VPC. All traffic through a Cloud VPN tunnel is encrypted using IKE version 1 or IKE version 2 and travels over the public internet, though with confidentiality guaranteed by the IPsec encryption layer. Google Cloud Platform offers two variants of Cloud VPN. The first is Classic VPN. Classic VPN uses a single VPN gateway with a single external IP address and supports a single tunnel per gateway. It offers a 99.9% uptime SLA. Classic VPN is legacy and should not be used for new deployments because it cannot meet enterprise availability requirements and does not support dynamic routing via BGP. The second and recommended variant is HAVPN, which stands for High Availability VPN. HAVPN is designed for 99.99% availability. It achieves this by deploying two VPN gateway interfaces, each with its own external IP address, hosted in separate physical infrastructure. To reach 99.99% SLA, you must create two tunnels, one from each HAVPN interface on the GCP side to a corresponding interface on the peer VPN gateway. HAVPN requires dynamic routing through BGP and works exclusively with Cloud Router. The diagram shows the HAVPN architecture. The GCP VPC contains an HAVPN gateway that has two interfaces, Interface 0 and Interface 1. Each interface has a unique external IP address. On the peer side, whether that is an on-premises VPN device or another cloud VPN endpoint, there is a corresponding peer VPN gateway also with two interfaces. Tunnel 0 connects GCP Interface 0 to peer Interface 0. Tunnel 1 connects GCP Interface 1 to peer Interface 1. Two cloud routers on the GCP side maintain BGP sessions over each tunnel and exchange route information dynamically with the peer. If either tunnel fails, traffic automatically reroutes through the surviving tunnel, which is how the 99.99% SLA is maintained. The VPC is connected to the HAVPN gateway, so all on-premises routes learned via BGP appear in the VPC route table automatically. Cloud Router and BGP. Cloud Router is a fully managed GCP service that provides dynamic routing for VPCs using the Border Gateway Protocol, known as BGP. Cloud Router is not a physical router or a virtual machine. It is a control plane service that runs as part of GCP's infrastructure and manages the exchange of route information between your VPC and external networks connected through Cloud VPN or Cloud Interconnect. BGP is the standard protocol used between autonomous systems on the Internet and in enterprise networks to exchange reachability information. In the context of GCP, Cloud Router acts as a BGP speaker that maintains sessions with the peer router on the other end of a VPN tunnel or interconnect attachment. When the peer advertises a route, for example a prefix for your on-premises network, Cloud Router automatically installs that route into your VPC's routing table as a dynamic route. Similarly, Cloud Router advertises your VPC subnet ranges to the peer, so the on-premises side learns how to reach GCP resources. One powerful feature of Cloud Router is custom route advertisements. By default, Cloud Router advertises all VPC subnet ranges to the BGP peer. You can override this behavior and advertise specific custom prefixes instead, for example to advertise a summary route that covers multiple subnets, or to advertise the IP range of a Cloud NAT gateway so on-premises clients can route return traffic correctly. The diagram walks through this flow. The Google CPVPC is connected to a Cloud Router. The Cloud Router maintains a BGP session over the tunnel or interconnect link to the peer router at the on-premises or partner side. The peer advertises its prefixes, shown as the on-premises routes flowing into the Cloud Router. Cloud Router installs those learned routes as dynamic routes in the VPC route table. At the same time, the VPC subnet routes flow from the Cloud Router to the peer, so the on-premises network knows how to reach Google CP subnets. This bidirectional dynamic exchange is what makes Cloud Router essential for any hybrid connectivity scenario. Cloud DNS. Cloud DNS is GCP's managed, authoritative domain name system service. It provides highly reliable and low-latency DNS resolution backed by the same infrastructure that runs Google's global DNS systems. Cloud DNS serves two primary use cases: hosting public DNS zones for internet-facing domains, and hosting private DNS zones for internal GCP and on-premises name resolution. A public zone in Cloud DNS is authoritative for a domain accessible from the Internet. When you create a public zone and add DNS records, Cloud DNS answers queries from anyone on the Internet for those records. It is fully programmable through the Cloud DNS API, gCloud CLI, or Terraform, making it easy to automate DNS record management as part of infrastructure deployment pipelines. A private zone is visible only to specific VPC networks you authorize. Private zones are used for internal service discovery. For example, resolving internal host names like database.internal or api.prod.internal to private IP addresses. Virtual machines in the VPC query their metadata server at 169.254.169.254, which routes DNS queries to Google's internal resolver, which in turn answers from the private zone records. This enables clean internal naming without exposing any DNS information to the public Internet. Cloud DNS also supports DNS peering, which allows a VPC to forward DNS queries for specific zones to another VPC's Cloud DNS resolver. This is important in shared VPC and hybrid connectivity architectures. Additionally, Cloud DNS supports inbound and outbound DNS forwarding through DNS server policies, which lets GCP virtual machines resolve on-premises hostnames by forwarding queries to on-premises DNS servers, and lets on-premises clients resolve GCP private zone records by querying forwarding endpoints inside the VPC. The diagram shows the Cloud DNS resolution flow. A virtual machine makes a DNS query. The query hits the GCP internal resolver. The resolver checks whether the queried domain matches a private zone, in which case it answers from internal records. If the domain matches a forwarding rule, the query is forwarded to an on-premises DNS server to resolve internal on-premises host names. If neither applies, the query is answered from a public zone or falls through to the public Internet's recursive resolvers. Cloud Armor. Cloud Armor is GCP's managed DDoS protection and web application firewall service. It integrates directly with GCP's external HTTP and HTTPS load balancers and protects Internet-facing applications from a wide range of network and application layer threats. Cloud Armor operates at Google's global network edge, the same infrastructure that absorbs some of the largest DDoS attacks ever recorded, meaning protection is applied before malicious traffic ever reaches your backends. Cloud Armor uses security policies to define rules that are evaluated against incoming requests. A security policy is attached to a backend service on your load balancer. Rules within a policy can match on IP addresses, CIDR ranges, geographic location, HTTP headers, cookie values, URI paths, query parameters, and more. Rules have a priority and an action of either allow or deny, evaluated in order from lowest priority number to highest, just like GCP firewall rules. One of the most powerful features is the pre-configured web application firewall rules. These are managed rule sets provided by Google that protect against common web vulnerabilities defined in the OWASP Top 10, including SQL injection, cross-site scripting, local file inclusion, remote file inclusion, and more. Rather than writing custom rules for every attack type, you enable these pre-configured rule sets and Google keeps the signatures updated. Cloud Armor also provides adaptive protection, which uses machine learning to detect and alert on potential application layer DDoS attacks by learning your normal traffic patterns and flagging anomalies in real time. When an attack is detected, adaptive protection can automatically suggest or apply blocking rules. The diagram shows the protection flow. Client traffic from the Internet arrives at the Google Edge, Cloud Armor's inspection point. Cloud Armor evaluates the security policy rules against each request. Requests matching a deny rule or dropped at the edge, never reaching your infrastructure. Requests matching pre-configured web application firewall rules for attack signatures are similarly blocked. Clean traffic that passes all rules is forwarded through the HTTPS load balancer to the backend services running your application. This edge-based architecture means your virtual machines and application servers never see malicious traffic at all. VPC Flow Logs. VPC Flow Logs is a Google CP networking feature that captures metadata about the network flows traversing your VPC network interfaces. A flow log record contains information about the source and destination IP addresses, source and destination ports, protocol, number of bytes and packets transferred, and the start and end timestamps of the flow. Flow logs are enabled per subnet and sampled at a configurable rate from 5% to 100% of all flows. VPC flow logs are written to Cloud Logging, where they can be queried, filtered, and exported to BigQuery for large-scale analysis, to cloud storage for long-term retention, or to a third-party SIEM such as Splunk or Elasticsearch via pub/sub. The raw flow records in Cloud Logging are queryable in real time, making it possible to investigate security incidents and network anomalies within minutes of their occurrence. Flow logs are valuable for several use cases. For network forensics and security incident response, they provide a detailed audit trail of all network communications. You can trace exactly which source IPs were communicating with a compromised virtual machine and what data volumes were transferred. For cost optimization, flow logs reveal expensive cross-region and internet egress traffic that could be eliminated or reduced through architecture changes. For compliance, they provide the network telemetry audit trail required by standards like PCI-DSS and HEPA. The diagram shows the VPC flow logs pipeline. Virtual machines inside the VPC generate network flows as traffic passes through their interfaces. The VPC Flow Logs agent, which is part of Google CP's hypervisor infrastructure, not a virtual machine agent, samples the flows and writes flow log records to Cloud Logging. From Cloud Logging, the records can be routed through a log sync to BigQuery for SQL-based analysis, to cloud storage for archival, or to pub/sub for streaming to external SIEM systems. Security analysts and operators query flow data from these downstream stores for monitoring, forensics, and compliance reporting. VPC Service Controls. VPC Service Controls is an advanced GCP security feature that allows you to define a security perimeter around Google Cloud resources such as cloud storage buckets, BigQuery datasets, and Cloud Spanner instances to mitigate the risk of data exfiltration. Even if an attacker compromises a service account or user credential, VPC Service Controls can prevent that attacker from copying data out of your protected environment to an external project or destination. A service perimeter is the core construct. You define which GCP projects belong inside the perimeter and which Google Cloud APIs are protected by it. Once a service like cloud storage is inside a perimeter, access to it is restricted. Only requests originating from within the perimeter, meaning from virtual machines, service accounts, or users that are inside the perimeter projects, are allowed. Requests from outside the perimeter, even with valid credentials, are denied. VPC Service Controls uses Access Context Manager to define additional conditions on who can access perimeter resources. An access level is a set of conditions including device trust level, IP address ranges, geographic location, and identity. You can configure a perimeter to allow access from outside under specific conditions. For example, allowing on-premises clients over a dedicated interconnect to access protected resources while still blocking access from arbitrary internet clients. There are two modes of operation. In enforced mode, all policy violations result in access being denied. In dry run mode, violations are logged but not blocked, allowing you to test the impact of a perimeter configuration before enforcing it, which is a critical safety measure before going to enforced mode in production. The diagram shows the perimeter architecture. Inside the service perimeter sit the protected projects and the Google APIs they use, such as cloud storage and BigQuery. Requests from a virtual machine inside the perimeter to those APIs are allowed. Requests from an external project or from the public internet to the same APIs are blocked by the perimeter, even with valid OAuth credentials. An access level allows exceptions, for example, A request from an on-premises network over interconnect that meets the defined access conditions can be granted access across the perimeter boundary. This creates a network-aware, context-aware security layer on top of IAM for the most sensitive data environments. Cloud CDN. Cloud CDN, which stands for Content Delivery Network, is GCP's managed service for caching and accelerating delivery of web content and APIs to end users around the world. Cloud CDN integrates directly with GCP's external HTTPS load balancer and leverages Google's globally distributed edge points of presence, referred to as POPs, to serve cached content from locations physically close to the end user, dramatically reducing latency and offloading traffic from your origin servers. The core mechanism of Cloud CDN is caching. When a user makes a request for a resource such as an image, a JavaScript file, or an API response, Cloud CDN checks whether a cached copy of that response exists at the nearest edge POP. If it does, this is called a cache hit, and Cloud CDN serves the content directly from the edge without contacting your origin backend at all. If no cached copy exists, this is a cache miss, and Cloud CDN forwards the request to the origin backend, retrieves the response, caches it at the edge for future requests, and returns it to the user. Cache keys determine how Cloud CDN identifies distinct cacheable objects. By default, the cache key is the full request URL. You can customize the cache key to exclude query parameters, include or exclude specific headers, or include cookies, giving fine-grained control over caching behavior for dynamic content scenarios. Cloud CDN supports several cache modes. The USE_origin_headers mode respects the cache control and expires headers set by your origin server. The cache_all_static mode automatically caches static content based on content type regardless of origin headers. The force_cache_all mode caches all responses for a specified TTL, overriding origin headers. Signed URLs and signed cookies allow you to restrict access to cached content to only authenticated users, which is essential for serving private media or paid content. The diagram shows the Cloud CDN request flow. A user makes a request. That request arrives at the Google Edge POP nearest to the user. Cloud CDN checks its cache. If there is a cache hit, the content is returned directly from the edge. The origin backend is never contacted. If there is a cache miss, the request is forwarded through the HTTPS load balancer to the origin backend service. The response is returned to the user and simultaneously stored in the edge cache for subsequent requests from other users in the same region. Identity Aware Proxy, IAP. Identity Aware Proxy, or IAP, is GCP's Zero Trust Application Access Service that controls access to your applications and virtual machines based on user identity and context, rather than network location. Instead of using a VPN to allow trusted employees onto your corporate network and then letting them reach internal applications, IAP sits in front of the application and validates every access request against Google's identity platform before allowing any connection through. IAP works at the Google Edge for HTTP and HTTPS applications served through GCP load balancers. When a user tries to access an IAP-protected application, their request hits the GCP load balancer, which forwards the authentication challenge to IAP. The user must authenticate with a Google identity, either a Google Workspace account or a Cloud Identity account. IAP then checks whether the authenticated identity has been granted the IAP Secured Web App User IAM role for that specific resource. Only if both authentication and authorization pass does IAP forward the request to the backend application. The backend application receives the user's identity in signed headers, so it can further personalize or audit without re-authenticating. IAP for TCP tunneling extends zero trust access to non-HTTP workloads. It allows you to SSH into a GCP virtual machine or RDP into a Windows virtual machine without giving the virtual machine a public IP address or opening firewall rules for SSH or RDP from the Internet. The IAP tunnel authenticates the user's Google identity and establishes a TCP tunnel through Google's infrastructure to the virtual machine's private IP. This eliminates the need for bastion hosts or VPNs for administrative virtual machine access. The diagram shows the IAP access flow. A remote user attempts to access an internal application. The request reaches the Google Edge where IAP intercepts it. IAP sends the user through the Google Identity Authentication flow. Once authenticated, IAP checks the IAM policy. Is this identity allowed to access this resource? If authorized, IAP forwards the request to the backend application running on GCP, injecting the verified identity headers. If not authorized, access is denied at the edge. The backend virtual machine has no public IP and no open firewall ports for external access. It is fully private and only reachable through the IAP-controlled path. Packet mirroring. Packet mirroring is a GCP networking feature that captures copies of network traffic from selected virtual machine instances or subnets and delivers those copies to a collector destination, typically a security monitoring tool, an intrusion IDS, or a network performance analyzer. Unlike VPC flow logs which capture metadata about flows, packet mirroring captures the actual full packet contents, including headers and payload, giving security and operations teams complete visibility into network communications for deep inspection. Packet mirroring is configured through a packet mirroring policy, which defines three things: the mirrored source, the collector destination, and optional traffic filters. The mirrored source can be a specific set of virtual machines instances, a subnet, or virtual machines matching specific network tags. The collector destination is an internal load balancer fronting the security or monitoring tool instances that will receive and process the mirrored packets. Traffic filters allow you to narrow mirroring to specific protocols, IP address ranges, or port numbers, reducing the volume of mirrored traffic and the load on collector infrastructure. Packet mirroring is implemented at the hypervisor level, meaning it operates independently of the virtual machine's operating system and cannot be detected or disabled by software running inside the virtual machine. This makes it highly reliable for security monitoring. A compromised virtual machine cannot suppress its own packet mirroring. The mirrored packets are encapsulated and delivered to the collector without affecting the original traffic path or introducing latency on the mirrored virtual machines. The diagram shows the mirroring flow. Source virtual machines generate network traffic as normal. They are completely unaware of the mirroring. The packet mirroring policy configured in GCP captures copies of that traffic at the hypervisor. Those packet copies are delivered via the mirrored traffic path to the collector internal load balancer, which distributes the mirrored packets across a set of collector virtual machines running an IDS, IDS/IPS, or network forensics tool. The original traffic continues unaffected on its normal path. The mirroring is transparent, lossless from the perspective of the original communication, and operates at line rate. Hybrid connectivity. Choosing the right option. Choosing the correct hybrid connectivity option for connecting your on-premises environment to GCP is one of the most consequential network architecture decisions you will make. The right choice depends on four primary factors: required bandwidth, acceptable latency, security and compliance requirements, and budget. Cloud VPN with HAVPN is the entry point for hybrid connectivity. It is the fastest to deploy, requires no physical hardware procurement, and costs significantly less than dedicated circuits. It provides 99.99% availability when both tunnels are active. The trade-off is that VPN traffic travels over the public internet encrypted with IPsec, so throughput is limited to around 3 gigabits per second per tunnel pair and latency is subject to internet variability. VPN is the right choice for organizations with moderate bandwidth needs, non-latency critical workloads, and a need for rapid deployment. Partner Interconnect is the next tier. It provides a dedicated circuit through a service provider with bandwidths from 50 megabits per second to 50 gigabits per second, at latencies consistent with a private circuit rather than the internet. It does not require your data center to be physically co-located with Google, making it accessible from nearly any facility. It is the right choice when VPN bandwidth or latency is insufficient, but a full dedicated interconnect is either not available or not yet justified by traffic volume. Dedicated interconnect is the highest tier. It provides 10 gigabits per second or 100 gigabits per second per physical circuit and can be bundled to 200 gigabits per second aggregate. It requires your equipment to be physically present or cross-connected in a Google colocation facility. It offers the lowest latency and highest throughput of any GCP hybrid option and is the right choice for organizations with very large data migration needs, latency-sensitive applications like financial trading systems, or compliance requirements that mandate dedicated private circuits. The diagram maps each option across the decision dimensions. Cloud VPN sits at the lower end of bandwidth with internet-based connectivity. Partner Interconnect provides dedicated private circuits up to 50 gigabits per second through a provider. Dedicated Interconnect provides direct circuits up to 200 gigabits per second. All three options use Cloud Router and BGP for dynamic routing. The diagram helps visualize which choice fits which combination of bandwidth and latency requirements, making the selection process clear and systematic. Traffic Director, Service Mesh Control Plane. Traffic Director is GCP's fully managed service mesh control plane, built on the XDS API, the same open API used by Envoy Proxy and Istio. It provides advanced traffic management, load balancing, and observability for microservices running on GCP, whether those services are deployed on GKE, Compute Engine virtual machines, or Cloud Run. Traffic Director manages the Envoy sidecar proxies or standalone Envoy proxies deployed alongside your services and pushes traffic configuration to them dynamically without requiring restarts or configuration file changes. The core value of Traffic Director over traditional load balancers is that it operates at the service mesh layer, inside the cluster, between services, rather than at the edge. Traditional load balancers handle north-south traffic, meaning traffic entering from outside the cluster. Traffic Director handles east-west traffic, meaning service-to-service communication inside the cluster. This allows it to implement fine-grained policies such as traffic splitting for canary deployments, fault injection for chaos engineering testing, circuit breaking to prevent cascade failures, retries with configurable backoff policies, request-level timeouts, and mutual TLS between services. Traffic Director integrates with Google Cloud Platform's global load balancing infrastructure, meaning it can distribute service traffic across backends in multiple regions simultaneously, performing global load balancing for internal services in a way that is not possible with regional internal load balancers. It uses the Google Cloud Platform health checking system to monitor backend health and automatically shifts traffic away from unhealthy backends across regions. The diagram shows the Traffic Director architecture. Traffic Director acts as the XDS control plane, pushing route configurations, cluster definitions, and endpoint updates to the Envoy proxies running as sidecars alongside the microservice pods. Service A makes a call to Service B. Instead of that call going through a traditional load balancer, it goes through Service A's local Envoy sidecar. The Envoy proxy applies the traffic policies pushed by Traffic Director, selecting the appropriate endpoint of Service B, applying retries if needed, enforcing MTLS, and recording telemetry. This gives you fine-grained, programmatic control over every service-to-service communication in the mesh. Google CP Network Architecture Best Practices. This final slide in Part 3 brings together the most important network architecture principles for production Google CP deployments. Applying these principles consistently across your Google CP environments prevents the most common networking mistakes and builds a foundation that scales securely as your organization grows. The first principle is to always use custom mode VPCs with a deliberate IP address plan. Define your entire IP address space, VPC ranges, subnet ranges, pod ranges, and service ranges, before creating any infrastructure. Reserve space for future expansion. Never use auto mode VPCs in production because you lose control over address allocation and risk overlaps with on-premises networks. The second principle is the principle of least privilege for firewall rules. Every firewall rule should target the minimum scope of virtual machines using network tags or service accounts, allow only the specific protocol and port required, and have a documented justification. Use firewall insights regularly to identify and remove rules that are overly permissive or have never been matched. Enable firewall rule logging for all deny rules to capture potential security events. The third principle is to eliminate unnecessary external IP addresses. Every virtual machine that does not need to accept inbound connections from the internet should have no external IP. Use Cloud NAT for outbound internet access, private Google access for API calls, and IAP for administrative SSH access. This minimizes attack surface dramatically. The fourth principle is to plan hybrid connectivity for redundancy. Never rely on a single VPN tunnel or single interconnect circuit for critical production traffic. Use HAVPN with both tunnels active, or use redundant interconnect links to different colocation facilities. Use Cloud Router with appropriate BGP timers and MED values to control failover behavior. The fifth principle is to monitor continuously with Network Intelligence Center, VPC flow logs, and CloudArmor analytics. Network security and performance are not set and forget. Regularly review topology changes, investigate unexpected inter-region flows, and audit firewall rules against the principle of least privilege. Thank you for your attendance. Please consider subscribing to the channel and liking this video.